In this video, we're going to talk about simplifying radicals. When we have a square root symbol with a non-perfect square inside the radical, the value is an irrational number. In math, we generally want to minimize the irrational portion of that value by simplifying the radical. There are two methods of doing this. The first one we'll explore is method number one. Now, there's actually more than two methods perhaps, but we'll talk about two of them. And it doesn't matter which one you become comfortable with using. In method number one, we're going to express the quantity being square rooted as the product of prime numbers. We're going to put that product of primes underneath the radical in the place of the number being square rooted. Then each time that a prime factor appears twice underneath the radical, we're going to eliminate them from underneath the radical and then place that factor one time in front of the radical. And at the end, we're going to multiply any factors outside the radical and place the product outside the radical, or in other words, in front of it. And then we're going to multiply any factors inside the radical and place the product inside the radical. So let's show this example. We want to simplify the radical square root of 98. Well, we know that the square root of 98 is we know that 98 equals 14 times 7, and we can break down 14 into 2 times 7. And so what we've now done by saying 98 is 2 times 7 is expressed it as a product of prime numbers. So we can now say, therefore, that the square root of 98 is the square root of 2 times 7 times 7. Now notice that 7 appears as a factor twice inside the radical. What we can do is put it once in front of the radical. So twice on the inside equates to once on the outside. We put it once on the outside of the radical, in other words, in front, and then we keep the 2 underneath, and we can say it's equal to 7 square root of 2. Now the radical square root of 96, there's different ways to break this down. We'll all have the same ultimate prime number decomposition, but someone might start by saying 96 is 12 times 8. Someone else might start by saying 96 is 48 times 2. But if you keep on breaking it down into more and more prime factors, ultimately we'll come to the same conclusion. So in this example here, 96 is 12 times 8. We know that 12 is really 6 times 2, and 8 is really 4 times 2. Well, 2 is a prime number, so we can't break that down any further, but the 6 can be expressed as 2 times 3, and the 4 can be expressed as 2 times 2. And what we now have is 96 expressed as the product of prime numbers, 2 times 3 times 2 times 2 times 2 times 2. So what that allows us to do is then say, therefore, that the square root of 96 is equal to the square root of 2 times 3 times 2 times 2 times 2 times 2. Now notice we've got the 2 appearing twice here, so we can pull that in front once. And we have this, another couple of 2's. We can pull those in front as well. And so we'll have a 2 times 2 in front of the radical. Now, inside the radical, we'll be left with a 3 times 2. And so our answer will ultimately be 2 times 2 in front of the radical 3 times 2. Now, we can simplify, and we just simply multiply what's in front. 2 times 2 is 4, and we multiply what's behind. 2 times 3 is 6, and we get our final answer of 4 root 6. Now, what if we want to simplify the radical square root of 450? Well, we break down 450 into 50 times 9. 50 is the same as 25 times 2, and 9 is the same as 3 times 3. Now, that 25 right there, that's the same as 5 times 5. So what we really have is 2 times 5 times 5 times 3 times 3. Now, regardless of how one gets there, we'll all agree if we do it correctly on the ultimate prime number decomposition. So that tells us that the square root of 450 is equal to the square root of 2 times 5 times 5 times 3 times 3. Now, we see that there are two 5s as factors on the inside and two 3s as factors on the outside. And so what we can do is bring one of those 5s in front and one of those 3s in front. So these two 5s on the inside become one 5 in front. These two 3s on the inside become one 3 in front. And we're left with just a 2 on the inside. And now we just simplify by multiplying the 5 and the 3. And we get 15 square root of 2. Now that was method 1. And method number 2 requires a bit of number sense. We recognize perfect squares. Now perfect squares include the numbers 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, etc. If you're not sure where those numbers came from, 4 is 2 times 2, 9 is 3 times 3, 16 is 4 times 4. So that's where all these numbers are coming from. Now, this is number sense. The more perfect squares you recognize, the easier this method is. If a perfect square is a factor of the quantity under the radical, then we can re-express the quantity under the radical as the product of two values, one of which is the perfect square. And then what we do is we recall that the square root of a times b is equal to the square root of a times the square root of b. This is a property of square roots. And so at the end then we simplify. So if we wanted to simplify the expression square root of 50, what we want here is some number sense. Do we recognize any perfect squares that are factors of 50? And the answer is yes. 25 is a perfect square, and 25 is a factor of 50. So we can re-express the square root of 50 as the square root of 25 times 2. That's equal to the square root of 25 times the square root of 2. And now we simplify. The square root of 25 is a known quantity. It equals 5. And so we just get the answer 5 root 2. Next, we have this expression here, square root of 1800. Now, out there somewhere, someone might recognize, hey, this is just 900 times 2. And that's equal to the square root of 900 times the square root of 2. And they might recognize right away that the square root of 900 is 30, and they get 30 root 2. So someone might be able to do that really quickly, get the correct answer. And that's great. But what I want to show you here is what would happen if you didn't recognize right away that 900 is a perfect square and a factor of 1800. What if it took a few more steps? The answer is it would be fine. So right away, imagine we started with the square root of 1800 and we said, you know what? That's equal to 900 times 2. Now, 900, if we don't recognize it as a perfect square, that's the same as 9 times 100. And then we say to ourselves, hey, the square root of 9 times 100 times 2 is equal to the square root of 9 times the square root of 100 times the square root of 2. Now, most people recognize the square root of 9 as 3, and most people recognize the square root of 100 as 10, and then we still have the square root of 2 hanging out. Of course, we multiply 3 times 10 and we get 30 root 2. Now, generally, I tend to use method 2, but you can use method 1 before, or you can even use a modified version of method 1. But if you're asked on a test to simplify a radical and show sufficient work to justify that you didn't need to use a calculator, then you actually need to show sufficient steps to justify you didn't need a calculator. It wouldn't be enough just to say, well, I got the answer right. It might be possible you just know how to press buttons on a calculator. And we want to test a little bit your number sense here. So now let's say we want to simplify the expression shown. Well, we're going to rearrange and collect like terms. Now, before we do that, I'll just mention that the square root of 2, the square root of 3, the square root of 2, and the square root of 3, they cannot be simplified because there's no way to reduce square root of 2. So what we're going to do is we're going to rearrange and collect like terms. So we begin with what we were given, and then if we want, we don't necessarily have to show this, but we'll rearrange this plus 6 root 3 and this plus 4 root 2 and make it plus 4 root 2 and plus 6 root 3. And now we're in a position to collect like terms. Determining a simplified version of 7 root 2 plus 4 root 2 is really the same as determining a simplified version of 7x plus 4x. And determining a simplified version of positive 6 root 3 minus 11 root 3 is no different conceptually than figuring out a simplified version of positive 6y minus 11y. So ultimately what we get is 11 root 2 minus 5 root 3. And when we collect like terms like this, don't change the values under the radicals. In the collecting stage, we don't do that. Now, what if we wanted to determine the distance from the point negative 6,5 to the point 4,1? Well, we might remember from grade 10 math, we have a formula for that. It's just going to be x2 minus x1, which is 4 minus negative 6, quantity squared. And we're going to add that to 1 minus 5, y2 minus y1, quantity squared. But we're going to put all of that under a square root. So what we get is the square root of 100 plus 16. That's the same as a square root of 116. Now, a perfect square that divides evenly into 116 is 4. So instead of saying square root of 116, we can say square root of 4 times 29. Now, the square root of 4 is 2, and the square root of 29 can't be helped, and we're left with 2 root 29. Now, what if we have a right-angled triangle with perpendicular sides that have lengths of 9 centimeters and 6 centimeters? Well, in that case, what we want to do to determine the perimeter, we want to get the length of that hypotenuse. So we just imagine a triangle, right-angled, and we want to determine the length of that hypotenuse. We know that we can just say c squared equals a squared plus b squared. So that's c squared is 9 squared plus 6 squared, so ultimately that equals 117. Now, that makes c equal to the square root of 117, but of course we want to see if we can simplify that. Well, a perfect square that divides evenly into 117 is 9. So we have the square root of 9 times 13. That's the same as the square root of 9 times the square root of 13. Well, the square root of 9 is 3, so we have 3 root 13. So that means that the perimeter, if you go back and look at our triangle, we have a side length of 9, a side length of 6, and a side length of 3 root 13. To determine the perimeter, we just add those values together. We can add like terms. The 9 and the 6 are like terms. They're both integers. That gives us 15. We can't add 3 root 13 with anything else in the way that we do with collecting like terms, so we just leave it. And the final answer is 15 plus 3 root 13. And of course, that's in centimeters. And we can do this example as well. We can evaluate the first bracket times the second bracket. Now, what we're going to do here is do the distributive property. The first thing we're going to do is multiply 9 times 5 root 3, and we get 45 root 3. What we're doing there is multiplying the outsides and the insides. So 9 times 5 is 45. That goes in front. And then inside, there's no radical with the 9. If it helps, we can think of it as square root of 1. But really, if you have an integer times a radical, just remember to bring the radical along. So we have, so 9 times 5 root 3 is 45 root 3. Then we do 9 times 4, and that's a simple integer question. That's positive 36. Now, this next one's kind of interesting. We do negative 2 root 3 times 5 root 3. And what we're going to do, we're going to multiply the negative 2 times the 5 to give us the negative 10. And then we're going to multiply the insides, the square root of 3 times the square root of 3. That's going to give us the square root of 9. And then we're going to multiply negative 2 root 3 times 4. So again, negative 2 times positive 4 is negative 8. And then we still have that root 3 as well. Okay? And so what we do is we say, notice when we multiply two terms, we multiply the portions outside the square root and we multiply the portions inside the square root. Now, the square root of 9 is highlighted in blue there. Every once in a while when you do this method, you're going to come up with a radical which actually can be square rooted to an integer or otherwise simplified. Well, the square root of 9 is 3, so we could just evaluate this right away. But however we do it, we say, I'll show you there in blue, it says negative 10 root 9, and now we're just calling it negative 10 times 3. And then negative 10 times 3 will just be equal to negative 30, and we show that in blue. And now all we're going to do is collect like terms. We've got 45 root 3 minus 8 root 3. That's going to be 37 root 3. In the collecting like terms phase, we don't change anything inside the radical. And then we have plus 36 minus 30, and that's going to be plus 6. Okay, and we show it there with the highlights.